Hi, I am Mohit Agarwal. I am doing PhD from Penn University, Noida, Greater Noida, and I am trying to explain Nebase and its applications. This is some theory and some examples. The abstract is that it is a very needed problem in current scenario to predict the text category of a new data from existing text categories. In this presentation, I tried to explore Bayesian probability approach to predict the class of a new text. It uses the probability that new text belongs to which category with the numeric score. The maximum score will tell which category the new query text belongs to. This process is easy and works to good accuracy. The introduction of naive-Bayes is it is also known as naive-Bayes classifiers. It works on the assumption that one features are statistically independent of one another. Unlike many other classifiers which assumes that for a given class there will be some correlation between features, naive-Bayes explicitly assumes the features as conditionally independent. While this is an overly simplistic distinction on the data, in practice, naive-Bayes is competitive with more sophisticated techniques and enjoys some theoretical support for its presumption. Because of the independence assumption, naive-Bayes classifiers are highly scalable and can quickly learn to use high-dimension features with limited training data. Thus, it is useful for many real-world datasets where the amount of data may be small in comparison with the number of features for individual piece of data such as speech, text, and image data. Examples of modern applications include recommendation systems, spam filtering, automatic medical diagnosis, medical image processing, vocal emotion recognition, etc. I have tried to explore example with naive-Bayes, which have two symptom files. One is conjunctivitis and one is cough. Each file is having patient symptoms which are 255 in numbers, and it will be recording patient symptoms in the file in a text form. For example, I have one line from conjunctivitis file which is watery eyes and itchy nose, one line from cough and the sneezing and coughing began. Similarly, one line from conjunctivitis, my eyes are so watery. Which categories of symptoms I have red eyes and nose belong to? Since naive-Bayes is a probabilistic classifier, we want to calculate the probability that a symptom I have red eyes and nose is cough and the probability that it's conjunctivitis. To get the probability, we need to convert text to numeric values. For this, we can use word frequencies by counting distinct words and total words and use them to compute probabilities. Now, what is Bayes theorem? Bayes theorem is a probability theorem which tells that probability of event A given event B is equal to probability of event B given event A into probability of event A divided by probability of event B. In our case, we have to find P of cough given I have red eyes and nose. So using this, we can reverse theorem. We can reverse the statement and say P cuff given I have red eyes and nose equal to P I have red eyes and nose given cuff into P cuff divided by P I have red eyes and nose. Now, what is the probability comparison? Since for our classifier we are just trying to find out which category has a bigger probability, we can discard the divisor, which is same for both disease, and just compare P I have red eyes and nose given cuff into P cuff. But similarly for conjunctivitis. This is better since we could actually calculate these probabilities. What is naive-Bayes theorem? It can be seen from the following equation that P of event Ck given x vector events is equal to P x vector events given Ck into P of Ck divided by P of x vector event. Now, since we know that x1, x2 are independent, we can write this as P of Ck given x1, x2 till xn is proportional to P of Ck into P of x1 given Ck into P of x2 given Ck into so on till P of xn given Ck. The naive part. The naive part is that every word in the sentence is independent of one another. This means that we are no longer looking at entire sentences, but rather at individual words. We write this as P I have red eyes and nose equal to P I into P have into P red into P eyes into P and into P nose. What is conditional probability? This assumption is very strong but works very useful. It makes the model work very well with little data or more data. The next step is just applying this to what we had before. P I have red eyes and nose given cuff equal to P I given cuff into P have given cuff into P red given cuff into P eyes given cuff into P and given cuff into P nose given cuff. Now all of these are individual words actually show up several times in our training set and we can calculate them. Calculating probabilities. The final step is to calculate every probability and see which one turns out to be larger. The calculating a probability is just counting in our training set. For example, p cuff will be the number of lines in cuff file divided by total number of lines in both the files. Then p nose given cuff means counting how many times word nose appears in cuff samples divided by total number of words in cuff. However, we run into a problem because if red doesn't appear in cuff sample, then it will mean that p red given cuff will be 0. This will not help because we will multiply it and it will make the whole probability as 0. So we will have to do something different in this case, which is Laplace smoothing. Laplace smoothing is in which we add the total number of possible words to the total distinct words in both samples in the divisor, so that divisor will never be greater than 1, division will never be greater than 1, and we add the frequency of the word in a file with and 1 to it. For example, p I is given cuff equal to frequency of i's in cuff samples plus 1 divided by total number of words in cuff samples plus total distinct words in both samples. For example, I calculated it for p I is given cuff, which is 91 plus 1 divided by 3168 plus 1827 equal to 0.0184. Doing this, in this we get pi of red eyes and nose given cuff equal to 7.72 into 10 is for minus 17, and pi of red eyes and nose given conjunctivitis equal to 4.57 427 484108468 into 10 to the minus 14. Since our classifier sees that probability of conjunctivitis is more, so it will say that the disease is conjunctivitis. These are some of the differences in which the researchers have tried to explore Nebes and compared it with other means like TF, IDF, or K-means and some similar, and it helps them to feel that Nebes is a very useful way to text classify and helps them largely. This we can use it in our context, which can be suited for us, and thus I end up here. Thanks.